Today we'll talk about inverse functions. So let's take a look at the function f of x equals x squared. This is a function that takes in a number and outputs that number times itself. So if you give it the number 0, it will spit out 0. If you give it the number 1, it will spit out the number 1. Likewise, if you give it the number 2, it will give you 4. If you give it the number 3, it will give you 9. So you can make a table of values that will show you what the value of this function will be for different inputs. Now the inverse function to this is a function that undoes the effect of f of x. So think of it as a function that does the opposite action that f of x does. So in the case of this function, as you might guess, the inverse function would be the square root function. The square root function tells you, given a number, what number should be squared to give you that number. So in other words, if you give it the number 4, it'll give you back 2. And if you give it the number 9, it will give you back 3. So it's doing the opposite as f of x. Now notice what this means. This means that the inputs to f of x match up with the outputs of f inverse of x. And the outputs of f of x match up with the inputs of f inverse of x. Looking at the graph, you can also see that f of x and f inverse of x are each other's mirror images across the line y equals x. Now, at first this might be a little bit confusing as to why this is happening. But let's take a minute and think about what exactly is going on here. The graph of the function f of x equals x squared is simply all the points a, b, such that f of a equals b. That's what it means to graph a function. You graph every point a, b that makes the equation f of a equals b true. So you'd plot the point 1, 1 because f of 1 is equal to 1. You would plot the point 2, 4 because f of 2 is equal to 4. Because of the definition of what an inverse function means, when we're dealing with an inverse function, if f of a is equal to b, we know that f inverse of b will equal a. So in other words, if the point AB is on the graph of f of x, then point BA will be on the graph of f inverse of x. Now there are some things you have to be careful about here, specifically regarding domain and range, which I will talk about in a future video. But for the moment, just think about it this way. If the point a comma b is on the graph of y equals f of x, that means that f of a is equal to b. Now if f of a is equal to b, then by the definition of what an inverse function is, where it swaps the inputs and the outputs, then f inverse of b will be equal to a. So the point b comma a will be on the graph of the inverse function. What this means is that if the point a comma b is here, then if we simply swap the x and y coordinates and we get the point b comma a, that will be on the graph of the inverse function. So in general, the inverse function will have a graph that is flipped across the line y equals x compared to the original function. Let's take a look at a few specific examples of inverse functions. Let's look at a simple function like f of x equals 2x. This is the doubling function. Given an input, the output is simply double that number. This is a linear function. It's a straight line going through the origin with a slope of 2. So it looks something like this. Now, as you might expect, the inverse function of the doubling function is a function that gives you half of the input. So if f of x equals 2x, then f inverse of x equals 1/2 x. Now notice, this fits the property of inverse functions that f inverse of f of x should equal x. Now I know this is a lot of different things appearing in one equation, but don't be overwhelmed by the notation. All this is saying is that if we have our f of x, which again, remember, this takes in the input x and produces an output f of x, and then we stick that output into f inverse of x, we will just get back with our original x. So in graphical form, what this might look like is x goes into a function, f of x comes out, that goes into the inverse function, and what comes out of the inverse function is simply our original x. So after going through first f and then f inverse, we're back where we started. Okay. So this was an example of a linear function and its inverse. If I wanted to graph the inverse function, it would also be a straight line through the origin, but with a slope of 1/2. As you can see, as we would expect, they are each other's mirror images across the line y equals x. All right. How do we do this for somewhat more complicated functions? Let's say we have the function f of x equals 2x plus 5. What is the inverse of this function? Now I've noticed that a lot of people will write something like f inverse of x equals 1/2 x minus 5. At first glance, that looks like it might be right. You're doing the inverse operation of doubling by taking a half, and you're doing the inverse operation of adding 5 by subtracting 5. However, this is wrong. Don't write that. To see why that's wrong, let's do an analogy. So let's say you have a block of cheese. Now, you want to give this block of cheese to someone. Now, you're not just going to give your block of cheese directly as it is. That would be a little bit messy. So first, you're going to wrap it in some wax paper. Okay, so you've wrapped your cheese in some wax paper. Now, you're not just going to hand that wax paper to someone, so you're going to first put it in a nice wooden box. And then once it's inside your wooden box, you might put a bow on the box. Okay, now let's say you give your cheese to your friend. What steps do they have to go through to get the cheese? So let's first look at what you did. You had your cheese. And first, if we're thinking of this as the input to a function, the first function would be wrapping. The next function would be putting it into a box. And the next function would be putting a bow. And at the end, you end up with this very nice cheese present. Okay. But if your friend who receives the cheese wants to get the cheese, they're going to have to undo those operations that you just did. So they're going to have to first remove the bow. And then they'll be left with a box. So they're going to have to remove the box. And then finally, they will have to remove the wrapping. And then only then will they end up with the original cheese. So notice that in order to get back the original input, your friend had to undo each of your operations in the reverse order that you did them. You did first wrap the cheese, then place it in a box, and then place the bow on. Your friend had to remove the bow, then remove the box, then remove the wrap. So everything is happening in the reverse order. It's the same with numbers and functions. If you're trying to undo a series of operations, you need to undo them in the opposite order that they were done to the input. So if we have the function f of x equals 2x plus 5, what happened first? First, we had x go into a function. But what came out of that, this was originally the multiplying by 2 function. And what came out was 2x. And then 2x went into another function, which was the add 5 function. And what came out of that was 2x plus 5. Now, if we want to undo this, we have to undo everything in the opposite order. So if this goes into our inverse function, first we need to subtract 5. Then we'll be left with 2x. Then we will need to multiply by 1/2, or divide by 2. And what will come out of this is x. So once again, notice that the adding 5 and the subtracting 5 are inverses, and dividing by 2 and multiplying by 2 are inverses, but we had to do them in the opposite order. What this means for our function is that the inverse function of f of x equals 2x plus 5 is not 1/2 x minus 5. Rather, we first must subtract the 5 and then divide by 2. So the inverse function would be x minus 5 all over 2. Notice that this is close to, but different from, 1/2 x minus 5. This would end up being, in simplified form, 1/2 x minus 5/2, or 1/2 x minus 2.5. This same principle works with more complicated functions. So let's take a look at a more complicated example. Suppose we had the function f of x equals 2x cubed minus 8. And we want to find the inverse function. What you should not do is simply look at them in the order that they appear and try to do the inverse of each step. You need to find the order that the operations were done and then do those inverse operations in the opposite order from the way in which they were done. So you can try this mentally and think to yourself, well, what was the last thing that happened? The last thing that happened was subtracting 8. So first you're going to add 8 to your input. And then what was the next thing that happened? The next last thing that happened to x, to the input of the function, was being multiplied by 2. So you're going to have to divide everything by 2. And then the first thing that happened to the input was being cubed. So the last thing you do in your inverse function would be taking the cube root. Okay, so this seems to work, but imagine getting even more complicated functions with many, many different operations. It's going to be very hard to keep track of all that in your head. So one trick you can use is the following. Suppose we have f of x equals 2x cubed minus 8, and we want to find the inverse function. Now, as we mentioned earlier, the inverse function is simply a function where we're swapping each point a, b, the point b, comma, a. The old outputs become the new inputs, and the old inputs become the new outputs. So another way to think about that is that we are solving for, we are swapping the values of f of x and x, and then we're solving for f of x. Let's see what I mean. If we have f of x equals 2x cubed minus 8, the inverse function will be x equals 2 times f of x cubed minus 8. But then we need to solve for f of x. So what just happened? I swapped f of x and x from this function up here. They simply traded places because the old inputs become the new outputs and the old outputs become the new inputs. But then we want to get it in the form f of x equals something, so we need to solve for f of x. And notice when we solve for x, what you will naturally do is undo each of the operations that was done in the original function and do the inverse operations in the inverse order. So doing the same steps that we just did mentally up here, we are first going to add 8. So we will get x plus 8 equals 2 times f of x cubed. And we'll divide both sides by 2. Get x plus 8 over 2 equals f of x cubed. And then we'll take the cube root of both sides. And notice that we get the same answer that we did mentally up here. So here's an example of a word problem involving inverse functions. So here's a scenario in which we might have to use an inverse function. So according to this scenario, a person's income tax is calculated according to a certain function. So you could write a certain function that takes in as input someone's income and outputs their income tax. Okay. However, the last question is asking the opposite. If someone paid $35,000 in taxes, how much was their income? So the function that is described here, calculated by taking 25% of the person's income above $10,000, that is for getting to their income tax from their income. So it's getting their taxes from their income. However, the question asks you to find someone's income given their taxes. So it's asking you the inverse. So this calls for inverse functions. So let's just be clear what we're trying to find here. You could write a function f that takes income and outputs the amount of taxes that you need to pay. We want to come up with a function f inverse that takes in the amount of taxes that were paid and tells you what the income should have been. And these are going to be related in an inverse relationship. So you might think one way to do this is, well, actually, you don't need to find an inverse function. You can just set the amount of taxes paid equal to 35,000. So you could write 35,000 equals, and then whatever your expression for f of x is. In this case, 25% of the person's income above 10,000. So that would be 0.25 times x minus 10,000. So this is saying 25% of the person's income that is above $10,000. And here we are assuming x is going to be greater than 10,000. Now, if you solve this expression for x, then let's see, we could do it. You multiply both sides by 4, which is the same as dividing both sides by 0.25. So you would get 140,000 equals x minus 10,000. Add 10,000 to both sides, you would get 150,000 equals x. So you've just found the answer to this question without really even using inverse functions. However, you may think you didn't use inverse functions, but really you did. You used a special case of finding an inverse function for just the number 35,000, but these same steps would give you the inverse function for any x. So let's say instead of 35,000, you were given any arbitrary number, and you had to find the amount of income that corresponds to that amount of taxes. So instead of 35,000, you would just get some number that represents the taxes paid, and your job would be to find the original income. By doing the exact same steps that we just did to find the answer to this problem, you could find this for any arbitrary input. And that's exactly what an inverse function is doing. What it's doing is it's saying that now 35,000, this number here, or whatever we replace it with, is going to be our input. And then we're going to be solving for x, and that's going to be our new output, actually. So that's what it means to swap the x and the f of x. So if our original f of x equals 0.25 times x minus 10,000, finding the inverse function is all about making our output our new input. So we're saying, okay, our variable here, our input, is going to be the amount of taxes paid. And then we need to solve for f of x, and that's going to be our output, to determine what the original income was. And then doing the same exact steps, multiplying by 4, and then adding 10,000, we arrive at our inverse function. So notice that we could also write this as f inverse of x equals 4x plus 10,000. Notice that here it just says f of x. Here it says f inverse of x. This is a matter of notation, just be careful. Here this f inverse of x means that it is inverses with this function here. Here f of x is just being used as a generic f of x, a generic function. Down here, this -1 means that it is the specific inverse to the original function named f. So now we have found an inverse function that can take any amount of taxes and give us what the original input should have been.